Okay, so our third speaker, who you've already heard from but has not been officially introduced, is Dr. Alain Bouscayrol, who received his PhD degree in electrical engineering from the Institut National Polytechnique de Toulouse in France in 1995. Starting the next year in 1996 to 2005, he was an associate professor at the University of Lille, where he is now a full professor. From 2004 to 2019, he managed the French National Network on Energy Management of Hybrid Vehicles, the P-HEV network. And since 2015, he's been the coordinator of the CUMIN program, as well as the co-director of an international research lab called eCampus on Sustainable Mobility, as well as the coordinator of the PANDA project, the European H2020 project that he is going to talk to us about right now. So please take it from here, Dr. Bouscayrol.
Okay. Thanks, Mr. Chairman. It's my pleasure to present the result of our PANDA community, which is a very nice community, and we work in a friendly atmosphere. So PANDA stands for Powerfull, Advanced and Level Digital Architecture for Electrified Vehicles. Our consortium is composed of 11 partners from 6 European countries, from university to industry, including some SMEs. So the presentation is composed of 4 parts. First, overview of the PANDA. I will focus on the new simulation library developed within PANDA. I will give an example on battery electric vehicles, and I will finish by some PANDA perspective. So first, the global framework of PANDA. As presented before, when we develop the new innovative vehicles within the W model, there are many simulation tasks and many simulation tools that are used. And for example, one component can be developed several times with different models in different software, with different accuracy. And this lead to a low flexibility because of no reuse of the model. We have to redevelop. Low interoperability. There is a risk of mistake by translating one model to another model. And unfortunately, on the contrary of what is expected in the W model, it could lead to increase the development time. So the objective of PANDA is to develop an open access model organization of all the models to a fast exchange, whatever the task within the W models. In that perspective, we will develop a cloud of models that can share models for the different action. The global objective is to reduce the time to market by 20%. What is the difference between other methods? First, we will focus on what is called functional simulation. Most of the actual simulation tools are based on structural description. That means that you have a library of structural components and you connect the components. But in our case, we will use another approach, which is called a functional description. So that we are focused on the function on the component and not the structure. The drawback of this methodology is that the user has to pre-solve some conflict of association before the simulation. But the interest is that with this pre-work, we can achieve a faster simulation and also more flexibility. The second key point of the PANDA project is to develop a cloud of models. on the contrary of most of the actual ongoing project, we will not use co-simulation by interconnecting different software. We will use a common software with a cloud of model. The drawback is that each partner should learn the new software and the new method. The interest is that it will increase interoperability and lead to a faster simulation that could be very useful in real-time application. In order to achieve this goal, first, we will use the EMR formalism developed by University of Lille. It's a formalism to organize models. We will use also an industrial software, SimCenter AmSim from Siemens, in order to demonstrate that this method can be integrated in actual software tools. And we have 3 study cases: a battery electric vehicle from Renault, a fuel cell vehicle from another European project managed by Université de Bourgogne-Franche-Comté, and also a hybrid vehicle from Valeo company. So let's focus on simulation library. First, we use as a common organization formalism EMR, energetic macroscopic representation. EMR is a graphical formalism in order to organize, model, and control. It is focused on the exclusive use of integral causality, more related to physical behavior, on interaction principle that respect energy conversion between components. And we have some rules in order to systematically define the control scheme. So the control is in blue in this spectrogram, and the system is in orange and green. And moreover, we have some rules in order to achieve a model reduction for simplification of models. So EMR is a causal and functional formalism for control and model organization that leads to fixed input and output of each subsystem. This property is of interest for seamless interconnection of the different components. Because of the integral causality, it will lead to a low computation time in comparison with other software. And another key point is that because the input and output of each block is fixed, that means inside these blocks, you can have different level of accuracy for the different models. So SimCenter AmSim has been chosen by the partner to integrate this method and to show the possibility to integrate this method. It is a well-known advanced industrial tool specifically for automotive industry. And as most of the software, it is mainly based on structural library. That means that you have library of component and you pick and place a component and connect as it is in real life, as you can see in this figure. But within the perspective of PANDA, we are developing a new library, a functional library, in order to organize, model, and control in the same way based on the EMR philosophy. So we have achieved this new library. You can see the library with the different EMR pictogram that can be used. And we developed some help module and tutorials in order to help people to achieve that. So let us take a simple example, a very simple battery electric vehicles. After the modeling part, modeling equation, we should organize all the model according to the EMR rule with fixed input and outputs defined by the methods. and in the second time, we can systematically organize the control scheme in blue. And then using the EMR library, we can systematically transpose this model organization in the software. And if you look one component, for example, you can look how we can implement the equation of this component, but always respecting input and outputs defined by the method. And then we can get some simulation results using some driving cycle and look what happens in terms of energy consumption and so on. What is important in this method is that thanks to the fixed I/O input and output organization, each component or subsystem can have different level of model. For example, battery, we can have a low accuracy model and fast simulation for that, medium accuracy, high accuracy, and it is the same for other components. That means that we can very easily change a level of model in function of what we would like to study. All the models have been built by the partners and capitalized in a cloud with this common software. And now we are able to simulate the reference vehicle and of course other kind of vehicles by using the cloud. So the reference vehicle is battery electric vehicles, fuel cell vehicles, and plug-in hybrid vehicles. There are two ways to use this cloud of simulation. The first is to upload simulation file on a local computer and to run and work locally. It's called standalone simulation. The other possibility is that the user is connected to the cloud and built his model using some pre-model to work and to run the simulation in the cloud and to upload the results. It is called cloud computing simulation. What is important to highlight is some blocks, some elements could be defined in a black box approach in order to be sure that the people that ask this component can keep the industrial property. I will now present one example. Of course, we have simulated the three vehicles, but I will focus only on the battery electric vehicle. So the studied EV is the Renault Zoe from the group Renault. Globally, we can say that we have four main subsystems in interaction in the traction subsystem: the battery, the electrical drive, the chassis, including mechanical transmission, and the road. The Zoe is the one with 41 kilowatt-hour of lithium-ion battery and a permanent magnet synchronous machine of 65 kilowatt. And globally, the vehicle is a fixed gearbox and more than 1.4 ton. So in this slide, you have a very simple model and first level model of the system using EMR. In green, you have the energy sources, for example, the battery. In orange, you have the power conversion, including the electrical drive, gearbox, and so on. And in blue, you have the deduced control scheme, including some strategy in order to distribute the energy when braking. So based on this global organization, we can use the EMR library of SimCenter AmSim and to pick and place different models. And you can see in this slide that I have selected a more advanced model than in the previous slide for the electrical drive and the chassis. Let us focus on the battery. Within the PANDA project, we have developed and we are also developing different levels of battery model. You can see only two on this slide. The first one is a pure electric models, very simple models. And the second one is a model taking into account the thermal effects. Of course, it's more complex. But as you can see, all the models are strictly the same input and output, that means battery voltage and battery current. And all the models have been identified by experimental tests from the Vrije University of Brussels in terms of electrical parameter, thermal parameter, and so on. It is the same for the electrical drive. You can see only two models that has been developed within PANDA. The first one is a very simple efficiency map. It is a static model developed by Group Renault. And the second one is a more complex model. It's a dynamical models, including saturation effect of the flux. It has been developed by the University of Cluj-Napoca. And once again, input and outputs are exactly the same. In terms of electrical ports, it's battery voltage and current. In terms of mechanical ports, is torque and rotation speed. And in terms of control input, is the reference torque. That means that all the models can be interchanged very fastly and easily. Of course, the models have been validated. So Renault do some real driving cycle test on the track of RTR in Romania. And we use the velocity plots as reference for the simulation. And we compare simulation results and measurement on the real vehicles on different variables. I just present the energy consumption and state of charge of the battery. And we can see that there is few errors, and for the different driving cycle we test, it's urban, extra-urban, highway, and so on, we have an error on energy consumption lower than 2%. That demonstrates the fidelity of the simulation. Another study which also of interest is to compare the classical approach with the new one. Thanks to the SimCenter AmSim software that is based on a structural library, we can compare a structural classical representation of the vehicles with the one with EMR. And using the same level of accuracy of each model and using the same control, we have achieved a reduction of the computation time by 15%. So now some perspective about the future steps. We are working specifically on the demo car of Valeo company. Is a classical thermal car that is hybridized by adding two electrical machines, one in the rear, one in the front, and a battery and a charger. And the interest of this part of the project is to test the added electrical systems. So we would like to test the combination of machine and battery by simulating the other parts in real time and interacting between this tested subsystem and the other part of the vehicle, which is called hardware-in-the-loop testing. To do that, I will just take the example of the battery. So the battery developed by Blueway is interconnected by a power interface and a real-time simulator developed by Typhoon, which is connected to the cloud. There is two ways to do the test. The first is to upload the file from the cloud, the file that simulate the plug-in hybrid electric vehicles, and to run the test locally. The second way is to split the model of the vehicles to have one part in the local power interface, one part that run in the cloud, and to have some exchange between the data of both, and to do one part remotely. So in order to conclude, I would say that we achieve the cloud of model, and we use it in order to simulate the free reference vehicles. Nowadays, we are working on testing using the hardware-in-the loop method, the electrical system of the plug-in hybrid electric vehicles. And we have to estimate the time to market reduction that is able to have using that method. And moreover, I will finish to highlight that we are estimating all the CO2 emission due to the PANDA project by the travels, computing, the equipment, and we will achieve some mitigation action. Our PANDA will use. Thanks for your attention.
Okay, excellent. Thank you. So I will remind everyone that you can ask your questions through the Q&A button or the chat functionality if you're having some trouble with the Q&A. And while I let people ask questions, I'll start with this one, that the models that you described, the cloud-based modeling approach, seems potentially very useful for a modern world where people are working across industry and academia, especially in a world where there's a pandemic. It's difficult to collaborate in person. And it might be a great platform for different people to share detailed models, you know, of a battery, for example, or someone else's detailed model of a motor. To what degree is the platform accessible to people, or will it be accessible in the future?
So we hope that we can have an open method. So we are working on the method. The simulation platform is just a demo, but the method could be used in different software. Anyway, we are working on an open platform. The key success of that is to be able to respect the IP of some partner. So one of the problem is that to be sure that we can interconnect a black box model that respects the input and outputs from the method, and to keep the confidentiality when this black box is uploaded on the cloud, of course, or the other way is that people can use a standalone open models and replace in their own computer the new elements that they would like to test. One of the interests when we discuss with automotive supplier is that they can provide some set of vehicles and ask to people to play and to demonstrate that maybe there is a new component that could have an added value.
Okay, interesting. Okay, so we have a question here from Bernard Sputh, and the question is about the feedback time for hardware in the loop testing. So when you do a cloud-based hardware in the loop test in that testing mode, how do you exchange the data between the test bench and the cloud server?
Yes, it's really a challenging task, and we know that it's a sensitive issue. I suppose that Valentin will give some detailed response in this presentation because his project is focused on that. But globally, The idea is to identify what as the slowest dynamics that can be run on the cloud. And it's mandatory to have a fast dynamics locally. And moreover, what is also important is to have a safety management in case of interruption of the exchange data to save the test and to maybe stop the test in a safe way. But it's a challenging task, it's sure.
Interesting. So there's a few questions related to the way the platform functions from Abdullah Pam. And so I guess I'm going to rephrase this a little bit, but the two main questions are, how challenging is it to convince companies to share their detailed models in this cloud-based platform? And is there a form of protection? Like, can they just make it a black box, for example, so that a user can't see inside the model? And if it is a black box, what does that mean for other users that might have trouble using it, that I guess they wouldn't be able to change anything on the inside?
Yes, it shows that a key of success is to manage IP, industrial property. And we cannot convince people to use this method if they cannot keep the confidentiality of their model. Within the PANDA, we have the Valeo company that develop a new electrical drive. And of course, they will keep the confidentiality of this new electric drive. And they are developing a black box model that is only known by the engineer of Valeo. We have the input and output that is respected, and we play with this black box model. So it's possible to do that. Of course, in order to have a coherent simulation, maybe we have to be sure that the people that deliver the black box model know or give the kind of model. Is it a static model? Is it a dynamic model, in order to have a good understanding of what are the interactions between the other. But it's possible to do that, and we do that with one component.
I have another question from Thomas Wallet, who asks how many car manufacturers are interested in the method to do modeling with their products, that these sort of rapid testing could save time and money, and it seems like a potential path forward for the industry.
Today, in fact, most of the manufacturers are working on developing hardware-in-the-loop testing bench, more and more. There is some specific requests because there are some international companies with different departments in different countries. And it shows that there is an increased interest for cloud, for sharing models for simulation first, and secondly, maybe to use this platform to do some hardware in the loop in another country and so on. It shows that locally all the automotive manufacturers are working on that, but the future step is, could we do that with different remote locations? And I suppose that Valentin will also speak about that part.
Okay. So for a final question, the question is about challenges or possibilities to extend this to other transportation technologies or other systems in general, or is it possible to extend it to things other than tracking the energy flows through a vehicle?
It shows that at the University of Lille, we have already worked with a railway system, subway system, including all the supply system for a complete subway line. So it's possible to work on that philosophy. We have also worked on renewable energy system, and we have some teams that work specifically on that. So it's possible to extend that. One of the major issue is that it's not the classical thinking of development, because it's functional, and today more and more people use structural simulation tools that is very easy to use. You pick and place the different component and you start the simulation. But the drawback is that the solver does some understanding instead of you, and you lack this knowledge. And for testing, maybe it's important to keep the knowledge.
Okay, yeah, excellent. So we will all individually thank Dr. Bouscayrol from our respective offices, and we will press on for the sake of time